The first method I'm going to look at for solving this sort of problem is called the bisection method. So I want to consider f a continuous function defined on the interval ab. So this is exactly what if we think back to that graph that I was looking at before, I had chosen this sequence of values from 0.05 to 0.5, and the function was definitely continuous on that interval. So just something like that. And also, I want to choose that interval so that f of a and f of b have different signs. So again, in my example, I had f of a was negative and f of b was positive. Then there's a result from calculus called the intermediate value theorem. And this should just make a lot of sense. If on one side of my interval I'm positive and on the other side of my interval I'm negative, continuous function is, we think about that as a function that you can draw without having to lift up your pen. If I'm going to get from this point down to this point, I'm going to have to cross 0 at some point in between. It's cheating to go around like that. So if f of a and f of b have different signs, then there has to be some point x in the interval ab where f of x is equal to 0. And so bisection is going to be an algorithm for finding that point x. And so the idea is I'm just going to take my interval, and I'm going to split it in half and evaluate it at the midpoint. So this point c is just the average of the two endpoints. So that's the midpoint of the interval ab. And I'll evaluate the function at this point c. And so sine is a function where if the argument is greater than 0, I get positive 1. If the argument is less than 0, I get negative 1. And if the argument is equal to 0, then the sine of that is equal to 0. And so what this is saying is if the sine of the function evaluated at the midpoint is equal to the sine of the function evaluated at the left endpoint, then I'm just going to move that left endpoint to the midpoint. So I make my interval half as wide, because if I know that function, it's negative here, and it still will be, then it has to be positive at the other point. I now have a new interval that's half as wide, and it still has the property that the function evaluated at the endpoints, they have different signs. And then if the signs are not the same, then I just chop off the other half of the interval. So I have a picture on the next slide that will hopefully make this a bit more clear. And so it's a very simple algorithm. I just chop the interval in half. That's going to give me two subintervals. At least one of those subintervals is going to still have the property that the function evaluated at the endpoints is going to have different signs. So that becomes my new interval. And then I go back and do this again. So every time I'm cutting my interval in half. And then for an algorithm like this, it's something that is automated. So you need to have a stopping condition, because any interval, I can cut that in half. So if I just programmed this using steps 1, 2, and 3 the way I've written them down here, it will just run forever. It will get a very small interval, but it's still going to just keep going. So the stopping condition, I'm just going to use a very simple one and say when this interval, so if I take b minus a, so b was the upper endpoint, a was the lower endpoint, so this is just the width of my interval. When that gets smaller than some tolerance that I have to choose at the beginning, so I could say I want to know the answer within 1/1,000,000th. So then when this interval is smaller than 1/1,000,000th, I know every point in there is within 1/1,000,000th of the midpoint of that interval, so I can stop. So this is what bisection will look like. So I started off with 0.1 and 0.3, so that was my initial interval. Then I evaluate the function at 0.1 and the function at 0.3. And so at 0.3, the function is positive. At 0.1, the function is negative. So that's sort of my starting condition. This is a condition I want to always save as I'm going through the iteration, is that the sign of the function evaluated at one endpoint of the interval has to be the opposite of the sign of the function evaluated at the other endpoint. And then I'm going to evaluate the function at a point C that's halfway in between, so at the midpoint of the interval. And so in this case, f of c is less than 0. So since f of c has the same sign as f of a, then this is the half, the chunk of the interval AC. That's the part I want to chop off and throw away. On the other hand, the interval CB, since f of c is negative and f of b is positive, I know it has to cross 0 somewhere in that interval. So that's the interval I want to have. And now I'm just going to do this all over again, except I'm going to start with this interval. So when I assign c to my value a, and then I go back to the beginning, and I repeat the bisection process with just this interval on the right side here. So I think this is me just explaining that all in bullet points. So I calculate the midpoint, evaluate the function at the midpoint. I see that it's less than 0. So since the sign at the midpoint is equal to the sign at the left end, I now just move this point A over to 0.2. So my interval gets half as wide, but I still preserve this condition that the signs are different. So each step preserves the sign. So once I've made my new interval AB, so once I've updated my A here, I still have the property that the sign at that endpoint of the function evaluated at that endpoint is the opposite of the sign of the function evaluated at the other endpoint. So I'll go through a quick R implementation. One of the nice things about these is that they're not very difficult to code. So I made it even less difficult by not doing any error checking. So when I say error checking, this function is going to just run no matter what values I put into it. So I need to, on my own, make sure that f of a and f of b have the same sign. Otherwise, this will still do something. It won't be the bisection method if that's not true, but it's still just going to keep splitting this interval in half. But who knows what the output will be. And so all I'm going to do is, so I know b is going to be greater than a. So that's another thing that this isn't checking. I could put in -3 for b and +5 for a, and the function's still going to run. So while b minus a is greater than this tolerance value, and this is another nice feature of R. So if I want to have an argument here that you can change, but I don't want it to be required every time you run the function, I can put an equals here. And so this means if you call this function with 3 arguments, they're going to be interpreted as f, a, and b. And then it will, anytime it needs a tolerance inside the function, it'll just use this default value here. If I just put tol with no default, then every time you called the function, you'd have to put a 4th argument. And so it's pretty simple. It's just while this interval is wider than the tolerance, so this is before my stopping condition has occurred, I compute the midpoint of the interval and I store it as c. And then, so R has a sine function, which is handy, but be careful when I say sine. I'm not talking about sin sine. I'm talking about sign sine now. So if the sine of f of c is equal to the sine of f of a, then c is assigned to a. So I chop off the lower half of the interval. And the only other possibility, if they have opposite signs, is that I want to chop off the other half of the interval, because it's a very simple algorithm. You lose this half or you lose this half. So I don't have to check any other condition. I know if this is satisfied, I do this. Otherwise, I chop off the other half of the interval. And that's going to continue running. The interval gets half as long every time I go through this, so between this set of brackets and this set of brackets. And eventually, the interval will be shorter than this tolerance parameter. And so I just decided I would return the midpoint of that final interval as my best guess of the value that I can feed into this function f that's going to make f equal to 0. And so let's see how it works on, this is the same example that I solved just using the plot last time. So now, instead of f sig just being this thing evaluated a whole bunch of times from 0.05 to 0.5, I'm now going to make it a function. So it's a function of one variable, sigma. So everything else is fixed. And it's just going to give me the Black-Scholes call price at that value of sigma minus 7. So this is the thing that should be equal to 0 when I find the correct implied volatility sigma. And so now I just want to use this bisection. So bisection, this is supposed to be typewriter font, so it's supposed to look like this R code here. Bisection was just the name of the function that I had on the previous slide. So I want to use that function to solve f of sigma equal to 0. So the arguments, remember, were the function that I want to optimize, and then the lower endpoint and the upper endpoint of the interval where I want that to work. And so it returns 0.25117. So what was the linear interpretation again? No, but from the quiz question.
Mine was 1359.
Okay, 1359. So the linear interpretation was pretty close, I suppose. Yeah. 2511, 2513. 1359. So, okay. And so then we can check the computed solution. So this is always a good idea. So I'm going to take the solution that is supposed to make this thing equal to 0. So that should make the Black-Scholes call price for this equal to 7. So I'm going to plug that back into my function for the Black-Scholes call price. And now I get basically 7 to within 2 or 3 significant digits. So this time, if I were to round this, I would round this to $7.00. So a little bit better than the just plotting method.